In assignment 2.22, we continue to practice the relationship of the derivative to the original graph. So here we've got a piecewise defined function, and we want to read its derivative values. So in other words, we're simply looking for slopes of tangent lines. So at -1/2, look at the slope of the tangent. Here we have a linear section, and its slope is 1. At 0, we have a corner on the graph, so the left-hand derivative does not match the right-hand derivative, so we would say does not exist. There will be a discontinuity in the graph of our derivative. At +1/2, the slope of the tangent, it looks like we have a rise of -3 and a run of 1, so we've got a slope of -3. At 1, we've got another corner, so the left-hand derivative was -3, and our right-hand derivative looks like it's going to be infinity. So we have no tangent at another corner. Here we're doing a left-hand derivative because we're doing the left side as we approach 1 from the left side. So this is another way of doing exactly the same tangent we just did at 1/2, since the left side is in this linear section. But the right-hand derivative, as x approaches 1 from the right-hand side, that's where it appears that it goes to infinity. Now, we are only assuming. You might just say that it goes to a large number. So if you estimated that the slope there was +20 or 100, so here we're doing the best we can to estimate the slopes. At 3, it appears we've got this local maximum point with a smooth turning point. Horizontal tangent gives us a derivative of 0. And our left-hand limit as we approach 5, there I would say we're going to a vertical tangent again, but this time we're in a section where we've got negative slopes, so we would be going to -infinity. The right-hand derivative at 5 looks like it is a constant function, so a horizontal line has a slope of 0. F prime of 6, we are in that same section, same horizontal section, so another 0. But at 7, the overall derivative doesn't exist. The left-hand limit would be 0, and the right-hand limit appears to be -2. So there is no derivative at the corner. At 7.5, our slope here appears to be -2. All right, so those should help us. I think our next task is to sketch a graph of the derivative on this same function. So let me go section by section here. We're going to have some discontinuities because we can see that the derivative changed from +1 to -3. So in this first section, the slopes were 1. So we would come up with a horizontal section to our derivative. And then let me mark off some more tick marks here. Our next section between 0 and 1, the slopes were -3, so our derivative would be down here. And then we have our slope of +infinity in this section, and going to a slope of 0, and then -infinity. So I think our derivative should be coming down, and then we would curve here to switch to our negative slopes and going to -infinity. So we would have a vertical asymptote here where the derivative did not exist, and a vertical asymptote here on our derivative graph. And then between 5 and 7, we have a derivative of 0. And between 7 and 8, we had a slope of -2. So we would have a number of discontinuities. So make sure that you're using open circles to denote that. So our green graph here would be the graph of f prime of x. All right. fill in a conclusion for each. Now we're talking in general here about any function. If the first derivative is positive, then f prime of x must be increasing. If f prime is less than 0, the slopes are negative. That means f is decreasing. And those terms, by the way, are better than rising and falling. We mean the same thing, but in calculus, let's stick with increasing and decreasing. If our first derivative is 0 at some x coordinate, then f of x is, a couple things come to mind here, a local max, a local min, a saddle point, or in a horizontal section of a graph. So I think that would cover all of the possible ways that we could have a horizontal tangent. So remember that, of course, the whole function could be horizontal. And this saddle point, remember the example of that was x cubed, where the graph is increasing, but temporarily here it has a horizontal asymptote, tangent, not asymptote. If f prime of x approaches infinity at some x coordinate, then f of x is approaching vertical. Or we could say having a vertical tangent, or the tangent is approaching vertical. So then the value of the derivative would become undefined, would become infinity or negative infinity at a vertical section. Sketch a function that has a negative derivative from negative infinity to 0. And then it has a horizontal tangent when the derivative is 0. So we think horizontal tangent at 0. And then the derivative is greater than 0 on the right-hand side. Well, I think a parabola could be a good example. Has to be falling on one side, hit a slope of 0, and then rising. So this would be a typical example, not the only answer, but certainly the one that comes to mind first. You couldn't do an absolute value graph. Remember not to pick absolute value because we have to have a smooth turning point here. If we want to have a 0 derivative, it has to have a smooth turning point here. So at a corner, the derivative would not exist. So make sure that you don't choose something like absolute value there. All right, now we want to think of a function that has a positive derivative on the negative side. Then it has a vertical tangent. And at x equals 0. And then the derivative, oops, and it looks like I switched letters here. Let's try being consistent there. Let's maybe stick with all g primes. And then we want it to have derivatives that are positive again. So we want it to be rising, vertical, rising. So that sounds like a typical example that we know is our cube root function. So if g of x were the cube root of x, so it is rising, and then it has a vertical tangent, and then it's rising again. So that would be one example there. All right, if this is our graph of f of x, which graph could be its derivative? So here's the things I would notice. Here we know there's going to be a local max, a smooth turning point, so our derivative will be 0. But to the negative side here, we want the derivative. It's rising, so the derivative would have to be greater than 0. And here's another smooth turning point with a derivative of 0. But between these 2 points, the graph is falling, decreasing. So f prime of x has to be less than 0 in this section. And then our graph is rising again. So f prime of x has to be greater than 0. So that's probably enough for us to find our graph. We want it to be positive, negative, positive. Notice again here now we're going to start looking for these inflection points. And that at that inflection point we're going to reach the turning point on our derivative. So I can see that this letter C goes from having positive slopes, negative slopes, positive slopes. So remember that the derivative graph is the slopes of the original graph. All right, and a little review here to make sure that we don't let you forget your definitions. F prime of x, we have our 2 difference quotients. Make sure that throughout the year you keep these in mind. And the second one, I might write as f prime of a, since we're going to end up with a's in our answers. And you don't have to use these same letters, by the way. You should recognize these even if we switched from x's and a's. Sometimes you might see them with a's and b's, for example. So you should recognize the same format. All right, and then let's practice using one of those. We know the power rule here, so we know what our answer will be, of course. So here we're repeating. We've done this before, but we just want to make sure that we remember. So I will try to quickly do both of these. Let me first do f prime of x, and let me do the x plus h method. Limit as h goes to 0. So I'm going to put x plus h into my function. So there's the first term. And then we want to subtract f of x itself. All divided by h. And now I hope that you know that your coefficients when you're cubing a binomial, and you could distribute that 2 right away. Maybe I will do that. I hope you know from Pascal's triangle that our coefficients are going to be 1, 3, 3, 1. So I'm going to double everything right away. 2x cubed, and then 2 times the 3 will give us a 6x squared h. And then a 6x h squared, and then the 2 times the h cubed, minus 3x minus 3h, and then our 2 terms here, make sure we distribute the negative sign. You'll catch your mistake if you forget to distribute. Because, of course, we are expecting this 2x cubed to cancel with a negative, and we're expecting this positive 3x to cancel, so that all of our remaining terms now have an h in common, so that we can cancel and solve that 0 over 0. So we're removing our limit problem, our removable discontinuity. So take an h out of the remaining terms, cancel the h, and now we can do our limit by direct substitution. So make sure you don't write the limit symbol anymore. So our h terms are going to go to 0. And there we have exactly what we were expecting. And I will do our second function. Maybe here I'm just going to write the function again so I don't copy it wrong as I scroll here. All right, so our second definition, our second difference quotient is limit as x goes to a. So first we're going to take f of x, and then we're going to subtract f of a. All over x minus a. And we know what has to cancel here. And I chose this problem since we've done it before, just to refresh your memory. So we're going to rearrange these two terms. And we're going to rearrange these two terms, but remember the negative sign distributes, so this will be a plus. Oh, and I think I wrote an A there, and that should have been an X. Let's try changing that one. And a plus 3A. And now we can factor by grouping the first two terms. We factor the 2 out as a GCF, and I think, did I copy my question wrong? Anyway, I said I was going to copy it. Sorry, gentlemen, I have to go back. That should be a 2x cubed. So let's see if I can catch that before I get too far. 2x cubed, 2a cubed. So here we've got our cubes. All right. So now we're ready to factor the first two terms. 2 is the GCF, and then the x cubed minus a cubed factors into binomial and trinomial. And our next two terms, we can factor -3 as the GCF, so that we will also have an x minus a factor. Now, you could skip to the next step, but I'm going to show that x minus a is the GCF, just for those gentlemen who find it easier to see every step here. But I would be perfectly fine if you skipped right to the next step, because I think we could all see what was going to happen at this point, that now the x minus a's have canceled. And now we're ready to do our direct substitution. Let x go to a. So I'm not going to write the limit symbol anymore. Our x's turn into a's. So here we'll have an a times an a. And here we'll have 2 times 3a squared. So there's our 6a squared minus 3. So we come up with the same answer in both difference quotients.